Hey there, YOLO enthusiasts! Welcome back to the channel. YOLO26 has just been released, and this is not just another incremental update. It introduces a state-of-the-art approach to real-time object detection, especially for edge and low-power devices. YOLO26 is not just about architectural changes. Instead, it rethinks how detection models are trained, executed, and deployed in real-world systems. Before exploring the architecture, let's take a look at the key features of YOLO26. First, YOLO26 completely removes distribution focal loss, or DFL. While DFL has been effective in previous YOLO versions, it often complicated model export and limited hardware compatibility. By removing DFL, YOLO26 significantly simplifies inference and broadens support for edge and low-power platforms. Second, YOLO26 is designed as a fully end-to-end NMS-free detector. Unlike traditional pipelines where non-maximum suppression is applied as a separate post-processing step, YOLO26 generates final predictions directly from the model. This reduces latency, simplifies the inference pipeline, and makes deployment more reliable in production environments. Third, YOLO26 introduces prog loss combined with STAL, a new loss strategy that improves learning quality, especially for small object detection. Fourth, YOLO26 adopts a new optimizer called MuSGD. MuSGD is a hybrid optimization method that combines traditional SGD with advanced techniques inspired by large language model training. This results in more stable training dynamics and faster convergence. And all of these changes lead to a very practical outcome: up to 43% faster CPU inference, enabling real-time performance even on devices without GPUs. So, if you're ready to dive into YOLO26 architecture, hit that like button, subscribe if you haven't already, and let's jump right into it. Let's start by looking at the overall structure of the YOLO architecture. In general, the YOLO architecture is divided into three main parts: the backbone, neck, and head. The backbone is the deep learning architecture that acts as a feature extractor, responsible for learning rich representations from the input image. The neck combines and aggregates features extracted from different layers of the backbone, enabling better multi-scale feature fusion. Finally, the head is responsible for predicting object classes and bounding box coordinates, which form the final output of the object detection model. This architecture diagram is based on the YOLO26 architecture file provided by Ultralytics. The original architecture file can be found in the Ultralytics GitHub repository, specifically under Ultralytics CFG Models 26. Based on this configuration, the specific YOLO26 variant is determined by three key parameters: depth multiple, width multiple, and max channels. The depth multiple parameter controls the number of bottleneck blocks within the C3K2 module, and also determines whether a PSA block is included in the C2 PSA module, while width multiple and max channels define the number of output channels for each block. Next, we will walk through the model flow, starting from the input. The YOLO26 input is an image with 3 channels. From there, the input is passed into the backbone. The backbone starts with 2 convolutional blocks, each using a kernel size of 3 and a stride of 2. Using a stride of 2 reduces the spatial resolution of the feature maps. Next, we have the C3K2 block, one of the main components in YOLO26 responsible for feature extraction and refinement. In this C3K2 block, the n parameter is set to 2, multiplied by the depth multiple, with C3K set to false and E set to 0.25. Next, there is another convolutional block with a kernel size of 3 and a stride of 2, which further reduces the spatial resolution. This is followed by a C3K2 block, where the n parameter is set to 2 multiplied by the depth multiple, with C3K set to false and E set to 0.25. The output of this block is also connected to the neck. After that, there is another convolutional block with a kernel size of 3 and a stride of 2. This is followed by another C3K2 block, again with the n parameter equal to 2 multiplied by the depth multiple, but this time with C3K set to true. The output of this block is also connected to the neck. Next, the features go through a convolutional block and then into a C3K2 block, before being passed to the SPPF block. Following that, we move on to the neck of the architecture. We start with the SPPF block. SPPF, which stands for Spatial Pyramid Pooling Fast, is applied after the last convolutional layer in the backbone. In YOLO26, an additional feature is introduced in the SPPF block, namely the shortcut connection. This shortcut allows the input to be directly added to the output, helping preserve information flow and improve feature representation. After the SPPF block, the architecture continues with the C2PSA block, which stands for Cross-Stage Partial with Position-Sensitive Attention. This block enables the model to learn global relationships between pixels or features at different spatial positions, thereby enhancing the model's ability to capture richer and more informative spatial representations. Next, we have the upsample layer, which is used to increase the resolution of the feature maps. Similar to YOLO11, YOLO26 uses the nearest neighbor upsampling method. This method works by repeating the values of nearby pixels or elements of the input tensor to fill the newly generated pixels in the higher resolution feature map. In this case, the upsample layer is applied to the output of the C2PSA block to match its feature map resolution with that of the corresponding C3K2 block. The upsampled feature map is then combined with the features from the C3K2 block using a Concat operation. When using the Concat operation, the number of channels is summed, while the spatial resolution remains unchanged. This concatenated feature map is then passed through another C3K2 block. After that, the feature map from this block is upsampled to match the resolution of the next C3K2 block. Using another Concat operation, the upsampled feature map is combined with the features from that C3K2 block. This concatenated feature map is then passed through another C3K2 block. The output of this C3K2 block is then used as an input to the detect block. This block is specifically designed for small object detection. The output of this block is also forwarded as an input to a convolutional block with a kernel size of 3 and a stride of 2. The resulting feature map from this convolutional block is then concatenated with the feature map from the corresponding C3K2 block. After that, the combined feature map is processed by another C3K2 block. The output of this block is used as an input to the detect block and is specialized for detecting medium-sized objects. The output of this block is also forwarded as an input to a convolutional block. Next, a concat operation is used to combine the feature map from this convolutional block with the feature map from the C2PSA block. This combined feature map is then processed by another C3K2 block. The output of this block is used as an input to the detect block and is specialized for detecting large objects. In YOLO26, this final C3K2 block uses only a single repeat, which is different from the other C3K2 blocks that use 2 repeats. In addition, this block utilizes attention blocks, which is a new feature compared to YOLO11. If you're curious about the new blocks in YOLO26, how it differs from previous YOLO versions, a detailed breakdown of each YOLO26 block, and how YOLO26 processes an image, make sure to click the link in the description. Thank you, and until next time.